Greetings, Caboose here. Welcome to part 2 of my series on the inner workings of BattleTech. Today we're tackling internal structure. On the surface it seems complicated. This is one of those subjects that is actually more complicated than it appears, so it seems complicated because it is. Now this was an area that I had some training on as part of my time with GM. We're going to not just jump into what structure is and what it does, but also different material and construction techniques and different applications for the end products. Structure is, in a broad sense, used to make the internal frame that everything in a given unit is attached to. It's sometimes also referenced as the chassis, but that's something fundamentally different. The chassis is the design, shape, and/or form factor, while the structure is what forms the foundation to attach everything you need to complete that chassis, as well as the basic shape and load-bearing capabilities. So, let's take a deep breath and jump right into it. As I mentioned, at its base level, structure is a form. That's really the most basic of tasks it performs. It gives you the basic form of what it is you're constructing. Everything that's built has some kind of underlying structure, from buildings and streetcars to tanks and battle mechs. It's obviously engineered to do different tasks depending on its application, so let's take a look at some of those. Buildings are relatively straightforward. They're what are generally considered statically loaded, meaning that the weight changes by a comparatively small amount at any given time. These are typically rigid, hardened materials that have little flex or give to them. Most of the loads buildings are meant to carry are compressive loads, meaning that they are compacting the materials used in construction. Those materials vary greatly from simple and organic materials like wood and even bamboo in some areas to more complex like reinforced ferrocrete and things like transparent aluminum or transpex windows. I'll touch on those in my armor video a little bit more. Structure in the case of buildings is also what everything else is attached to. Power leads, communication gear, and the outer finishing pieces like any kind of weather protection, windows, roofing materials, and in some cases armor and environmental sealing. In certain applications like hostile environments, think space, oxygen deficient atmosphere, or underwater, the structure of a building will also house backup power generation. This is typically rechargeable power cells or even housing a backup fusion reactor depending on its use. Space stations are also considered to be statically loaded structures, except they don't have to deal with changing weight, but instead changing mass. In space, this isn't as big a deal if you're a slow-moving or orbital station. Mass is generally a consideration only if and when your orbit needs to be altered in some way. Typically at those times, orbital stations will wait until they're low on supplies, general cargo, personnel, and possibly attached ships. Then they'll have their orbit altered and resume normal duties. Things like cars, interplanetary or interstellar ships, fighters, tanks, and battle mechs, to name a few, are based around dynamically loaded structures. This means in a nutshell that the weight they're supporting in any one area can change by a significant percentage at any given moment. These structures are not only engineered to flex and/or give a certain amount, but also to withstand high degrees of shock. As a quick note, flex and give are two different things. Shock is basically an impact. It imparts a high amount of energy in a short time span, typically measured in tenths if not hundredths of a second. This is where having a decent amount of flex is handy, as the material will temporarily deform as best it can to absorb or redistribute this energy. If it can't, that's when it gives. When a material gives, it either permanently deforms or just outright breaks. Think about hitting a baseball. The material, the bat, and the ball handle the impact very differently, but to the same net result. The bat is rigid. It transfers the energy down to the length of its structure to the wielder. The ball is much softer. It has a dense core but gets softer as you move towards the outside of it. It will flex until it absorbs as much energy as possible, which leads to it absorbing an entire impact and being propelled in the opposite direction. When the ball gives, it loses things like its stitching or some of the twine inside of it. When the bat gives, it's much more dramatic and generally results in breakage into multiple pieces with enough force to injure anyone nearby without adequate protection. So with that in mind, let's look at ground vehicles. Fundamentally similar, they have a basic frame that's more or less on a 2D plane. The main components are anchored to this: the power generator, motor, energy storage if that applies, and that kind of thing. Then, a supporting structure is added on top. This is where the passenger/crew go, as well as just about everything else. The body of the vehicle, electronics, armament, etc. This is engineered in a way that if it exceeds a certain impact rating, it's meant to deform rather than break. That absorbs the energy directed into it as much as possible, leading to less harm to the people inside. In the case of military vehicles, armor is also bolted onto this structure, becoming a temporary part of it and reinforcing it until it's no longer viable. Now, this makes it tricky to design a weapon that has equal effectiveness against both armor and structure. Typically, designers will just compromise on damage in exchange for consistent results on both. There are exceptions, however, that are specifically targeted at structure and meant to break it in new and interesting ways. We'll cover that in a later video, however. Dropships and jump ships share a lot of design characteristics, but I'm only going to touch on them briefly because they spend most of their time in space. Dropships being interstellar usually only have to worry about mass and being able to anchor a certain amount of it. They're capable of interplanetary flight, but very, very, very slowly. They are the urban mechs of spaceflight, taking weeks or months to go the same distance a transport dropship can cover in days. Dropships have to worry about weight and mass, and this is the reason why once they exceed a certain weight, they're almost all spherical or elliptical in shape. Curved or rounded objects are very good at transferring weight to another object. In the case of dropships, that would be the ground. Building things out of ellipses, better known as arches, has been around for millennia and likely will be around for many more millennia for the simple fact that they are efficient and they just plain work. Now, on to what everyone's been waiting for, battle mechs. To start, while most mechs are humanoid in shape, their structure only bears a passing resemblance to human bones. A good example of this is the wrist. A human wrist contains dozens of bones and is both an engineering marvel and nightmare. On a battle mech, however, it's typically somewhere between 2 to 5 bones depending on size. The torso is similar. Why have close to 40 bones when you can just use 3 or 4 solid pieces? Their backbones are also the same. They don't need to flex to enable the mech's upper body to curve. Nothing else would withstand that anyway, so it's typically just one or a few large rigid pieces. Everything else is pretty close to the same in scope. Massive leg bones, 1 piece for the upper arm, 2 or 3 for the lower arm, and the feet are typically multiple pieces just for the sake of needing to grip the ground they stand on, and for that they need to be articulated. Same with hands if present, and they need to be able to grip or grab things. But I hear you ask, what are all these different structures made of? Well, it varies not just depending on use case, but also on the money available for construction. Buildings are all very similar beyond the wood and extruded examples that are used mostly for civilian dwellings. They use a flexible rod or rebar as a matrix to form the rest of the structure around. Despite being around for thousands of years, steel rebar is still a popular material for this purpose. It has enormous tensile and compressive strength, it's cheap, and it can be engineered to have a high degree of flex before permanent deformation occurs. Also, if you place it in a horizontal load-bearing surface with an upward arch, when the structure is complete and loaded down, it gives it additional strength, not just due to the internal arch, but also because it resists straightening back out. The other materials are usually derivatives of concrete. Concrete is still used in some poorer areas due to the low cost of its components, but in most places ferrocrete is used. They are similar in many ways, though ferrocrete incorporates iron oxide into its composition. When combined with a couple well-known chemical reactions, this winds up absorbing CO2 during the curing process and also shortens the duration needed for it to be fully cured. Advances in material science has made it not necessarily stronger than regular concrete, but much more durable overall and resistant to wear. Windows, portholes, and similar objects are made up of any number of materials. Plain old tempered glass is still used, and when manufactured in space has much greater strength than when it's made in gravity. Transparent aluminum is also a popular one used in space vessels due to its impact resistance and ability to have sensors woven into it like many other metals. In combat vehicles, a material called transpex is used in a lot of cases. It's essentially an advanced plexiglass. It's rigid but compressible, which makes sealing it much easier. It's also ablative in nature, meaning that when trying to melt it, pieces of it will chip off. This is also great for impacts and explosives, as it mitigates the damage by scattering the energy and can still more or less be seen through after. In battlemech cockpits, it tends to have micro-reflective surfaces embedded into it for the purpose of scattering laser light, and when current is applied can also be darkened in sub-1 second time frame to prevent blinding of the pilot for whatever reason. Your run-of-the-mill civilian vehicle and even law enforcement will typically use a fairly plain stamped or extruded steel that's heat-treated to meet the needs of the vehicle. Steel is easy and cheap to make or repair, so until you get into heavy industrial or combat needs, it's pretty common. Battle mechs, industrial mechs, and combat vehicles use a lot of the same materials in their internal structure, just in different arrangements. The core of military internal structure is a foamed aluminum rod, beam, or bone, depending on the use case. It provides rigidity while also allowing it to flex under dynamic loads. Attached to it are silicon carbide fibers which allow it to resist deformation under extreme loads. Remember, mech pilots love to punch or kick other mechs, and the use of jump jets is quite demanding on the internal systems. Around that is a titanium sheath for additional protection, and it also houses some sensors for damage detection, allowing the battle computer to adjust how the mech or tank operates when it's received critical amounts of damage. In this regard, vehicles are pretty straightforward, and the decreased complexity also makes them more damage resistant. Ton for ton, it's a lot harder to critically damage a vehicle than it is a mech. All this structure tends to weigh quite a bit, reducing the overall weight any given chassis can carry. This necessitated alternate materials with more advanced manufacturing techniques to try to counter this limitation. Enter endosteel. Endosteel internal structure has the same base components, but it's manufactured in 0G. Obviously, this is quite complex and takes not only a large orbiting facility to accomplish, but also very precise control. They are able to decrease the overall density of the foamed aluminum core by, in a nutshell, adding more voids or bubbles. While this lightens the weight of the frame, it also greatly increases its bulk. This is similar to how, for instance, a kilo of paper doesn't support much of a load, but when you fold it and arrange it the same amount of paper in a particular way, you can stand on it with little to no signs of stress. This is mostly used in lighter mechs where you have less load-bearing capability but enormous amounts of empty space to work with. When you scale this up into heavier assault mechs, though, this extra bulk becomes more and more of a detriment and an internal layout nightmare. So, some adventurous boys at Solaris 7 came up with an alternative they dubbed Composite Structure. Composite Structure has a lot of similarities to endosteel, mainly its reduced weight of roughly half. However, what they didn't do was increase the bulk of it to make up for the loss of strength. Instead, materials were blended into the mix or attached outside of it. Things like high-strength carbon filament and what could be generously called a secret sauce of different lightweight materials to make sure it had the same ability to hold up under dynamic loads. What it doesn't have is the same damage resistance of any other internal structure used. Now what that means to the pilot or driver is that if a hit breaches the armor, it will easily inflict twice the damage as it would on normal structure. A different group of enterprising individuals in Comstar went in the opposite direction. They decreased the amount of foam introduced into the batch of aluminum and added extra silicon carbide fibers and titanium sheathing. While it doesn't create any appreciable difference in how much load a mech can bear, and it doubles the weight, it also makes it incredibly hard to damage. This is known, quite plainly, as reinforced structure. It will endure roughly twice the firepower of normal structure types, making a frankly terrifying turn of events when the inevitable armor breach occurs, at least for whoever was expecting the mech to go down in short order. It does not, however, reduce the chance for other critical systems to be hit. It's important to note that as a result of wildly different manufacturing techniques, none of the structure types can be used to repair, replace, or even patch another type. They simply aren't compatible and can't be made to assist one another, much in the same way you can't weld a steel cable to a rope, and tying them together won't do you much good either. Nor can you replace select parts of the structure with different types. For vehicles, this would grossly affect their balance and ability to consistently maneuver. For mechs, this is even more pronounced. Because of differences in size and weight, if the mech was able to stand, which is unlikely, once it started moving it has a high likelihood of just straight up falling over. So folks, there you have it. A bit wordy and with a lot of engineering knowledge dropped. Structure in general is a marvel of engineering that is centuries, in some cases millennia in the making. Techniques and practices that were developed during the time of the Romans on ancient Terra are still alive and well, being used with little evolution needed. It's a fine example of how you can make exotic hardware using mundane materials and methods. I'd like to thank my dedicated and expanding viewers for their patience. It's remarkably hard to get pet projects done during the holiday season, but rest assured, when I get the spare time, I am working on them. The next video in the series will be about my bread and butter when I worked for GM, and that is armor. It stops weapons, it protects against the environment, but at the same time a well-placed blow or unlucky fall can shatter it like glass. Truly fascinating stuff, and much more complicated in terms of material science. Until next time, farewell, and maybe I'll see you on the Moose, stop! You can't use an Atlas femur as a club.
Swinging the leg is the best way to improve my dragon.
I don't care if your mech can swing it, that's 6 months' salary.